So I want to show okay, so this so let's so what is the Poisson vector for this structure? Let us compute it. In the work there is no computation, but I do it because it's simple, so let's try to do it. So so I put x, no, sorry. What do I want? So I want to give, okay. So let's call this, let me call the coordinates on G star with xi star. So these are the coordinate xi star on this manifold, the global coordinates because it's a vector space. And then dxj star. And we compute the bracket. So this is the definition through the bivector, right? The one that we saw before. You remember the bivector? The generic bivector is like this. Now we write the definition in this way, and then with the Rubin equation to see what is the bivector. So. So this is the pairing between this. So I have to do the bracket of df psi. So I do d. Okay, what is df? What is df? So df is No, wait. I've made a mistake right here. I'm glad. So this will be summation df dxi star dxi star. Right, Stephen?
Yes.
This is what it is. I made a mistake. And then summation dg dxj star dxj star. Okay, so we do the pairing. Now this is, of course, the bracket. Now notice that this dxi star, these are differential forms on G star. So these are elements of G. The dual with respect to the coordinates. So this becomes bracket of no, I don't want to do that. So the pairing of summation df dxi star dg dxj star dxi star dxj star psi. This is what it is. Now, these are really the coordinates on. These are the coordinates on G. These are the basis for G, the algebra. So when I do this bracket, the structure constants will come in. So this will become like summation df dxi star dg dxj star, and then we have summation Cijk dxk star psi. Well, these are the structure constant of your Lie algebra. You know, if you have the Lie algebra, a little remark, if x1, xn is the basis for G, we define the structure constant as follows: I xj is equal to Cijk xk. These are the structure constant. Okay, so what do we see? We have that if we compare this, so this, what do I want to say is that, this is not chalk here, eh? No. Let me finish this because I feel guilty. So, see that we have and then I have dg dx j star, and then I have Cik, and really now we have the pairing dxk psi. Right? So this, so effectively, what is this? This is an element of G star, right? And this is an element of G. So this is nothing but psi evaluated at dx k star. This is what it is, right? So we have shown that this is this thing is pi ij psi. So it's the kth component of psi. So this is like psi k in the coordinate. So we have proven that pi ij is summation of Cijk psi k. Now what we have proven. So very explicitly depending on the structure constants. Well, you sort of guessed this, right? Because, I mean, this is inherited from the algebra. It has to depend on the bracket in some fundamental way. But this calculation tells us that once we know the bracket, we can explicitly write the Poisson bivector. So I added this because it seems it was more concrete. This is not concrete at all. Okay. I also wanted to make a remark, but it's very intuitive, I'm not sure. Maybe I'll wait the next time because I want to say more. I want to say at least what is a Poisson group. Maybe the chalk. Grazie.
Certo che non ci siano più gesti.
No, lo porto sempre con me, me lo sono dimenticata. Okay. So, we are almost there to define what is a Poisson group, which is the main character of this lecture. So, before we do this, I want to define, so if M1 and M2 are Poisson manifold, I want to give a Poisson structure to the product. So I want to show, so M1 times M2. So So this is the Poisson bracket of M1, and this is the Poisson bracket on M2. Okay, so if you have two Poisson manifolds, the product is a Poisson manifold in a natural way with this definition. Okay. And then the next thing, so this is one thing I want to say. Second thing I want to say is what is a Poisson map?
Dai avanti, che ti dico, va bene.
See? No, I just said that the product of manifolds is really. So what is a Poisson map? So if M1 and M2 are Poisson manifolds, this is nothing but no, sorry, what is a Poisson map? You want that F composed with F. So the bracket of so these are kind of silly things. What is Poisson manifold and also what is a Poisson submanifold? A submanifold is a submanifold of M, and when you restrict the Poisson bracket is well defined. That's all. Finally, the Poisson Lie group, which is what I was really after. So it's a Poisson Lie group if the multiplication is a Poisson manifold. So if now let us see explicitly what this means, okay? So what is the expression for the multiplication?
G must be a Poisson manifold, or are you speaking?
Poisson manifold. If yes. It's, if G is a Poisson manifold and this is I contracted two things, of course. So if I take a Lie group, it's a Poisson Lie group if it is a Poisson manifold, and furthermore the multiplication is a Poisson manifold. So let us see what this means. So I work this out. So the condition is the following. So you want so you're taking so I'm writing this condition. I'm writing this condition right here. For F being the multiplication map. Okay, I want to see the expression. What is the condition for M to be a Poisson map from here? So I want so this has to be equal to. So I'm taking the. So this is the Poisson bracket in G times G, and this, of course, he doesn't do anything like this. He gives the result. So this is F1, F2. So I rewrote the condition. Okay? This is very typographical. So it says Poisson map if it satisfies this condition. So if I have the multiplication, it has to satisfy this. Let's see what the consequences are. So this is obviously this is x times y, okay, and this okay. So let me write it in it's kind of a stupid way because so here it says. Now I have to use the bracket of g times g, right? So, okay, let's write an extra thing. So it will be f1, and then I do m, what does it say there? It says y. So this is my so this becomes so f1 is a function that lies where? f1 and f2 are functions infinity of g, right? So what you're saying is that you want the argument of your function has to be right multiplied by y. So you write like this, is rho y f1. So the rho y f1 is the function that takes x and associates f1 xy. Which is this thing, right? It's not happy. It's kind of a way of writing. It's nothing very intelligent. It's rho y f2 and the same plus lambda x f1 lambda x f2 equal f1 f2 xy. So we have found this. So the condition x, of course, x here and y here. The condition for G to be a Poisson group reduces, okay, G is a Poisson manifold and the multiplication has to have this property. So being a Poisson map, it is this property. If you right multiply by y and then left multiply by x, you get that. So it's more explicit in some senses, not okay. Okay, what is our degree of happiness here? Not very high. I mean, I gave only definitions.
So R2N with that Poisson structure is a Poisson group.
Yes, it's a Poisson group, the bracket is 0.
Right.
Right. So not very smart.
Right. But it is an example, right? It's like,
yes, no. What are the examples we're thinking of?
Right.
What are the examples? We're thinking about the classical groups. SL, GL is a Poisson, the orthogonal, they're all Poisson groups. What is there? Poisson structure structure. That's the next question. We will suffer a lot to get it.
Okay.
It won't be cheap.
Can we make an example without suffering so
No.
much?
We could make an example using quantum groups, because a quantum group inherits.
For example.
But then I'm not sure how many people here know quantum groups. That's the thing.
I know they're not groups.
They're not groups, right?
That's all I know.
But interestingly enough, if you have a quantum group, it'll give you a Poisson structure on the group that is quantizing. Suppose you're quantizing SL2, you get this quantum SL2, which is not a group, and gives you a Poisson structure on SL2. But unfortunately, Nicoletta, I'm not sure if it is less cruel to give quantum groups treatment.
This was not my suggestion.
No, I'm saying is, for me it's easier to get the Poisson structure through quantum groups, but again.
And what about the Lie algebra and the Poisson Lie group? Because that's the Poisson structure of the kind.
You have no patience.
No, I'm just...
Observation. So, what is the deal here? See, we have introduced, we've introduced an extra structure on the functions on G, right? So it's only reasonable to expect that you see on the tangent bundle, the G star acquires a structure. That's the thing. And this is how it is, in fact. And not only this, but it's if and only if. So we'll see that there is a Lie structure on G star, and if you have such a structure, you can bring back a structure on G of Poisson Lie group. So it's really, I'll show. So if G is a Poisson Lie group, we have natural structure of Lie algebra, canonical. On G star, where G is a Lie of G. So clearly, if we take the Lie algebra of our Lie group, it has a Lie algebra structure, of course. What I'm saying is that there is a canonical structure on the dual. What is this structure? So, this is not how he defines it. He defines it in a very different way, but the way he defines it, I don't agree. Well, it's not that I don't agree, it's crazy. I don't agree. So the definition is the following. You take the differential of the Poisson bracket of Fg and x, so you choose. So you have f and g in, so I should say what these things are. So x and y are in G star. I choose f and g in C infinity of G such that their differentials are x and y. You remember that the differential we saw it a minute ago. The differentials of C infinity, no, we didn't say that. We saw something slightly different. So df and dg belong to the tangent, right? Okay. So this can be effectively thought as elements of G star. And I take the differential of this evaluated at the identity. Again, this is the differential of something at the identity, so this is an element of E, G star, which is G star. So this is the bracket. And it's pretty obvious if we define it like this, that it satisfies all of the properties. The only non-obvious thing is that you have to prove that it's independent from the choice of f and g. This we sort of believe. Okay. So I think it's reasonable, right? You have Poisson group, you have a Lie algebra, and now you have structure on the dual. But then, see, you can push this further. What I'm saying now, it's everything he says, but in a totally different language. So if you try to read what he says, it won't look like at all. But I think it's more clear what I say. Is it clear what I'm saying there? The definition is clear. There is something to do, because it's not obvious that it's fine, but... Now, I want to push this further. See, because if you have this bracket, so another observation. So G Poisson Lie group. So we have G star is a Lie algebra, we just saw this. So it means that we have this thing, right? This is the bracket. This is what we just saw. Now, see, you can look at, see, well, let's say our field. Field is real or complex. We will use it both ways, doesn't matter. So, you see that this gives us a map from G to G tensor product G by duality, right?
Sorry, I was not listening. You take, what is G, what are you taking?
So,
what map are you taking?
I'm taking the bracket, right? And then I'm looking at the dual. So a map, so if I do it by duality, this gives me a map on the other side, on the other way. Right?
I was trying to understand the other.
No, it's just to explain to the students. It's like, so if this is an element, so this is an element psi on the dual. And every element like this gives you composing with that, right? Okay? It's something that we know. We know it, right? Happy? Sort of. At this hour, maybe not. But, and we call this delta. Now, I like my definition better than his definition. No, but Nicoletta, are you happy with the definition of delta?
Yes, I think you can make it explicit if you want to be clearer.
What do you mean explicit?
To say what delta is.
Yes, if you take an element psi, this is going to the one that takes psi, what I say. So I want to, what is the image of, I don't know, U and V. So this image will be psi composed. Is this. Okay? This is explicit. But the thing is that I'm using the double dual. The dual of a dual Lie algebra is the Lie algebra. It's vector space thing. It's not very smart. In fact, instead, he writes this other definition of delta. Book's definition of delta. It is the same as this one. So delta of an element is funny because it's the same, which is really tragic. They look the same, don't they?
What did you write? That is pi r? Pi what?
Pi r, no, see, he doesn't write the r. It took me like 2 hours. Because, so pi is a bivector, right? Pi is our Poisson bivector. Pi r is the bivector translated to the identity. So you move the bivector to the identity. So it is something like, so I don't know how you call it, right translation to the, so you move it. You transport your vector back to the identity. He doesn't write this little r. See? This is very disappointing because if you try to make sense of this expression without the r, it's a problem. But then I went to the Chavi Presley book and they have this definition for delta, which I think is much better. Then they give this theorem. This is the theorem that they give, and they put the r. So it's
Crazy.
No? Don't you think it's better this definition?
I think.
Yes, but Fabrizio, you are listening to us. Don't you like what you are making us study? Because this is what happens. Okay. No, but he knows I will, when he comes back, maybe a test for Fabrizio. He knows. No, it's true.
We can always change.
Yeah, look at that. No, you will not change until I finish to explain.
Not change subject, but change book.
Change book. No.
Also because there are many
Now you will
you started from the most difficult stuff.
No, I don't care. No, I mean, it says, read this book, I'm reading this book and giving you my lectures. And, okay. Now, si chiama vendetta. No. Appunto, ma verrà interrogato, cioè. Okay, so the thing is the following, that see, this delta will inherit many properties from the bracket. So this delta will have properties because it's coming from a bracket. So it's not just a matter from this to this. It will have extra properties. So these properties will be called the observation.
So, Rita, sorry, I'm a bit lost. So you started with the Poissonian group G.
Mm-hmm. So start from G.
You made that remark.
G star.
You noticed that you can define in a canonical way the algebra structure
on G star.
Okay.
Then
now you are considering this delta method.
Which is dual of this bracket. And notice that the fact that this is a bracket will have the Jacobi identity, will have some properties. So it will reflect on properties on delta, obviously. Right. So I'm writing down the properties, okay? So this is what delta does. So it does the following. So plus, minus, y. I write what this means, okay? So it's better. I should have written differently. Okay, whatever. I write like this. So this means, this is another way of writing the following, okay? You can also write like this, do the bracket, okay? It's a notation thing. Minus. Can we prove this? Yes, we could prove this. It will take us some time to prove this. So this fact requires some effort. But I'm saying that it's believable that this happens because this delta will have inside some properties because it's coming from a bracket. So it is not so absurd that it has. So it's not that any map that you write will, so it will come from this, so it will have some properties. This is called the one cocycle condition. Let's call this condition. Okay, so I will end this lecture with the one last definition. Which is sort of summing up all that we know. G is a Lie by algebra if is a Lie algebra and we have define this with cocycle condition. Okay, this is such that 1, its dual is a Lie bracket. Two, delta has one cocycle condition. So essentially, what we have done, we have a Poisson-Lie group. We notice that G is Lie algebra, has many properties. So G star is also the algebra, and then we can build this delta with, which is a cocycle. And then we say, okay, we define a Lie by algebra, something that behaves like a Lie algebra of a Poisson group. Now the question is any Lie by algebra the Lie algebra of a Poisson group? This is true, and this is due to Drinfeld. And we'll speak more about this. So it's a theorem, it's tough, it's not immediate, right?
And he uses quantum groups, I see.
I don't know, I may use, I'm not, Drinfeld's theorem, I found the proof in a quantum group book. But I'm not sure, I didn't read the proof, I just looked at the result. So I wanted to get rid of Poisson geometry because then there is more. We haven't constructed the Poisson structures on classical groups, so we will do it. I think I will take my body at home where I die. Grazie. Scusate, vado.